So let's try our hand at predicting another double displacement reaction, specifically predicting the products. Let's do that. Let's determine if it is indeed a precipitation reaction if a solid is formed. And then we're going to use this example to introduce the concepts of molecular, total, and net ionic equations. But first things first, let's go ahead and predict the products of this double displacement reaction. And with that and using the solubility rules, determine if it's a precipitation reaction. So let me get my little pointer, my little pen again, because I need to do my little crisscross to predict my products. And in a double displacement reaction, we said the cation of one species pairs with the anion of the other. And so in this case, for our first reactant, silver nitrate, Ag is the cation, and that polyatomic nitrate is the anion. And so I'm writing the cation and anion for that species, symbol and charge. And I'm going to do the same for the second molecule, cation and anion with their charge of that species. So then I can clearly see what gets paired with what. So specifically the silver, the Ag, is going to be paired with the Cl, and the potassium is going to be paired with the nitrate. And so those are the products of our double displacement reaction, which is shown here. And then we can determine the state by using the solubility rules that are on MindTap. I will give you a copy to use, obviously, for in lecture and for the exam. You see on those solubility rules that all nitrates are soluble, and species that are soluble in water get the state of AQ for aqueous. Species that are insoluble or do not dissolve in water get the state of S. S meaning solid. And looking for AgCl on your solubility rules, you see that it is insoluble, so it is a solid. So this is our balanced. It is balanced because number and type of atom on the left is equal to number and type of atom on the right. This is our balanced double displacement precipitation, because we formed a solid, precipitation reaction. And this kind of reaction in particular, we also can call a molecular equation. Molecular because all of the species involved in the reaction, reactants and products, are written as intact molecules. So that is the molecular form of this equation, which is obviously very handy to use, for chemists to use when doing stoichiometry and determining what products are formed. But it can also be important or also instructive to take a molecular equation and write it in terms of an ionic equation. And why would we want to do that? We'd want to do that because, as we learned earlier in this chapter, species that are soluble or strong electrolytes in water, they are not dissolved as intact molecules. They are disassociated, or they break apart into their component ions, specifically their cations and anions. So it can be instructive to take a molecular equation, which is what's shown down here, which we just talked about in the previous slide, taking that molecular equation and writing something called the Ionic equation. The Ionic equation, sometimes also called total Ionic equation. To write the total Ionic equation, you need to first have the molecular equation, and you need to focus on everything that is aqueous, that dissolves in water. Species that are aqueous or dissolve in water, those are broken up into their constituent cations and anions in the total Ionic equation. Species that are pure solids, like this silver chloride, or pure liquids or gases, those species, since they do not break apart into their ions, they stay together in the total Ionic equation. So for this particular molecular equation of silver nitrate reacting with potassium chloride to give solid silver chloride and potassium nitrate, we can write the total ionic equation, which I'm just going to call TIE down here, the total ionic equation by taking the species that are aqueous and splitting them into their cations and anions. And when I do that, you will see that I take each species and I write not only the symbol, but the associated charge and the associated state with it. So for example, a aqueous form of silver nitrate can be broken into the silver ions and the nitrate ions. Remember, nitrate's a polyatomic, it's a groupie, it stays together. So species that are aqueous get broken into their constituent cations and anions, which is what's done for the silver nitrate, the potassium chloride, and the potassium nitrate. Everything else, pure liquids, pure solids, and gases, stay together. And again, total ionic equation is important because it accurately represents what is actually swimming around in your beaker or in your test tube when you do the reaction. So that's total ionic equation, and you should feel comfortable being able to give the total ionic equation from the molecular equation. And then there's one other kind of ionic equation that we're going to talk about, and that is the net ionic equation. So still using the silver nitrate and potassium chloride example, I have here the molecular equation and the total ionic equation. Looking at that total ionic equation, you see that there's some similarity to reactants and products, meaning there are some ions that you see on the reactant side, specifically the nitrate and the potassium. There are some ions that you see on both the reactant and the product side. And just like you can do in algebra, if you have like terms on either side, you can simplify them by canceling them out. We can do something similar in chemistry with regards to ions that are on both sides of the total ionic equation. We can cancel them out to be left with something called the net ionic equation. So looking at our total ionic equation, we see that both sides have nitrate and potassium in common. Those can be crossed out Those ions are called spectator ions, those that are on both sides of the total ionic equation. Once you cancel out those spectator ions, you are left with the net ionic equation, which is essentially everything else after you cancel out the spectator ions. And so you see what I'm boxing here in red. What's left, what's boxed in red, is all that is listed or shown in the net ionic equation. And most of the time, particularly if you have a double displacement reaction that is a precipitation reaction, almost always your net ionic equation will be the chemical equation of the formation of that solid. So those are the concepts of molecular, total, and net ionic equations from double displacement reactions, specifically precipitation reactions. In the next video, we're going to talk through 2 more examples using those skills, being able to predict products and determine the molecular, total, and net ionic equations for 2 reactions.